All right, we are recording. We are moving. We got combinations and composition of functions today. We'll go ahead and title my page like a good student does. I don't know why I'm using my
Wow,
first name.
full name. Look at
Yeah,
that.
right. Date. Today is today, and this is a period between one and I don't need that plus sign. One and infinity. So before we get started, Mrs. Contreras, I am sharing my screen, right?
Yes.
Cool, and we are recording. We talked about before we started about what we've been doing in innovation period, and we've only been able to meet with one of the four pre-calc classes because they are our innovation period. But we wanted to bring something up, and that is taking care of yourself. So before we get started with this lesson, just real quick, we want to show you how we plan to take care of ourselves. So for me, and I need all you students and Mrs. Contreras too to hold me accountable to this, I am running 100 miles in the month of October. I am
Wow.
terrified. I am worried that, I need you guys to call me out so that I can succeed in this task because I want to take better care of my physical self. Mrs. Contreras, what are you going to do in the coming months to take better care of yourself?
So I have a goal of not running 100 miles because that's never, I think, going to be a goal of mine, but that's fine. That's great for you, Mr. Kirk. I would like to be able to do a 5-minute plank before Thanksgiving. So I'm at 1 minute right now. So it seems that every week I'll probably need to add at least 30 seconds.
30, that's a big jump. Do you think you could
I know.
increment it differently?
I don't know. I think I'll like instead of thinking about it week by week, I might do every couple days. I'll just increase by like 15
Mm-hmm.
seconds,
Mm-hmm.
10, 15, depending on how it's going.
A 5-minute plank. We need a video of the final day before Thanksgiving of you doing this plank and like screaming in pain and then succeeding because we are going to put that in our minds. We are going to know that we are going to succeed.
Or maybe I'll
Uh,
just do it during my virtual check-in hours on that day
mm-hmm.
before Thanksgiving. So if you want to see me do a plank, then you can come to virtual check-in.
Yeah, awesome. All right, good goals. All right, and we want you, viewer, student, to make a goal for yourself. Maybe it's physical, maybe it's mental, maybe it's emotional, but we want you to try to be conscious of your well-being, whether that be physical, emotional, or mental. So, running 100 miles, planking for 5 minutes. What are you gonna do? Let's go ahead and get started with some math. All right, let's move on from our our physical health and think about our mental ability, our ability to do math. Let's do this thing. The function machine. So we've kind of talked about this already. What a function is. You plug something into a function, and then it spits something out, a specific thing, a unique thing. That is a requirement for a function. Right? If you put x into this function, and two things come out, that's a great vending machine. I mean, those are the ones that you kind of abuse, and you get two Coca-Colas, but that's not a function. What happens when you plug in -9 into this function right here?
And that looks like it's a check x. Does that mean square root of x, Mr. Kirk?
Yeah, so I'm going to go ahead and add a little line here so that's clear that it's a square root, because this is maybe what you've seen before. But a lot of equation editors stop and don't give you that top bar. So I'm actually going to erase it now that we've said this, right? Be just weary that might be, let me zoom in real quick. This is not going as well as I wanted it to. But now you can see a little bit better here. The square root bar might end before it starts to move to the right above the radicand. All right. So let me go ahead and zoom back out, get full width. What happens when I plug in -9 into this function here?
I think that function machine is going to explode because
Explode? How do I
negative
draw an
9 is
explosion?
not. Oh, wow. Look at that. Boom.
Bam! Boom! Like, why is it exploding?
Well, because the domain of the square root function does not include -9.
You can plug in things between 0 and infinity, right? And -9 is not in there. So nothing comes out. I'm going to go ahead and write undefined.
Mm.
That's the term that we usually use when we're talking about domain restrictions. But yeah, that is undefined. And the reason why I have this example here is because we're going to progress through several different types of combinations of functions. Function addition, you can see right here. You'll see function multiplication on the next page, function division on the following page, and then finally function composition. All right, that's kind of what we're moving towards, this idea of composition. And we are going to care very much about the domain of these things. What's the domain of two functions being added together? What is the domain of the division of two functions? So domain is something that we're going to keep coming back to. So now that that's in our head, let's keep that there as we progress. All right, so let me go ahead and do one thing on my other screen. Awesome. Now I can see you. I wasn't able to see you before. That entire conversation we've had so far, I haven't been able to see you, but now I can.
I'm just making silly faces at you.
Oh. Well, I'll be able to watch this back, so I'll know. All right, so function addition. I have a diagram here. I think it does a pretty good job explaining what happens. Right? I have a function, the way we write it, just f plus g. And what this is saying is I have two functions. I'm plugging something into both simultaneously. Those two functions are going to evaluate that number simultaneously in separate worlds. And then they're going to come together, they're going to congregate, and then add their two outputs together. It's really important to think about that order of operations. When we have f plus g, let's go down and look at an example. We're plugging, here's our example right here. We're plugging in a number into both functions separately and then adding those numbers. Think about how that might affect the domain. What is the domain of my first function here, f?
That is all real numbers except for positive 3.
And I was about to write like a 0 or something, but let me go ahead and get that 3. Boom. And then let's move out. How did you know to get rid of that 3? Let's just make sure that it's clear, cookie cutter, no one is confused.
Yeah, because the domain, well, that would be whenever that function is defined. So the only time that it's not defined is when we have a 0 in our denominator, when x equals 3 equals 0, and that happens when x equals 3. X minus 3 equals 0.
I'm going to put some domain tips here at the top.
Ooh,
you just told me that we need to look for...
Make sure it doesn't get covered by our heads.
Oh, good point. Good point. Let me go ahead and put it... Cammy's eraser feature needs improvement. Let me go ahead and put them down here because I don't really need this space. But I am going to erase those. Domain tips. Right? Look for when the denominator is 0. I'm saying the denominator cannot be 0. Oh. So look for when the denominator cannot be 0. Those are going to be removed from your domain. All right. What's the domain of g?
The domain of g is 0 to positive infinity, and that.
We're trying to write the infinity in a normal way.
Hey, thank you. The 0 is included because you can take the square root of 0. It's just 0.
Mm-hmm. And then do we include infinity?
We cannot include infinity because have you ever seen infinity of sheeps?
Maybe in my dreams.
In your dreams? Really? You sleep that long?
Yeah.
No.
Or I can't get to sleep, so I count an infinity amount of sheep, and I never get to sleep.
But by counting, you are finding that it is countably infinite, the number of sheep.
That's fun. All right.
That's journal vocab.
Yeah, look up what it means to be countably infinite and not countably infinite if you're interested in some extension. All right, but how'd you know to cut out all the negative stuff just for domain tips?
Because I was looking at when the square root function is defined, and we were looking at before, -9 makes that function explode. We went from a boom to a bam.
Bam! All right, so negative numbers don't work in radicals, so I'm going to go ahead and say no negative radicals. All right, it can be 0.
As long as they're even roots, right? Because in a cube root, we can have negatives.
Wait,
or do you have another name for cube roots? Radicals are just...
Ooh, I hear you. Cube root. Yeah, you can have the negative of cube roots. We've graphed that function in the parent function lesson. And I was about to graph it wrong. I'm mad at myself. It's pretty much vertical there. Yeah. I really care about that difference for a reason that will come up later. All right, but no negative even roots. I was going to say square roots, but you're totally right. Even roots. Yeah, so 2, 4, 6, 8. Cool. All right, so that is the longer than that's maybe needed explanation of the domain of these two things, but that's what you're looking for as you proceed. When are we dividing by 0? Get them gone. When are we square rooting or fourth rooting or sixth rooting a negative? Get it gone. F plus G is 1 over x minus 3 plus the square root of x. All right, what's the domain of this thing?
Well, it would be wherever our two domains of our like separate functions are overlapping, right?
Yeah, right. And what do we call when we overlap in domains?
Overlap, intersect.
Intersect. Yeah, we want to look at when these two domains are intersecting. All right. We'll see why that actually very much matters in a later example in this lesson. But long story short, all you gotta do is boom, look at this, boom, look at this, and you got your answer. Right? I believe it's going to be 0 to 3. Get rid of 3. Okay, 3 works in the second one, but doesn't work in the first one, and vice versa. 3, 2. Let me do this for you.
It's very nice. You should keep doing it that way. Looks so good.
Yeah. I mean, maybe I'll get better at it. It's just 2 little circles is so much easier for me.
Growth mindset, Mr. Kirk. Growth mindset.
Growth mindset. I can dig it. Okay. So that's the idea, is we're taking the domain of the original functions and combining them, right? If I go back up to this picture here, when I plug something in, F needs to be able to output it and G needs to be able to output it. If that doesn't work, then if there's an explosion here, then the whole thing is exploding. I think we can agree, like the explosion is going to be big enough that it will have some residual damage over here. Undefined plus 5 is undefined. All right, let's proceed. Function multiplication, very similar picture. You plug in X, F operates, G operates, and then they come together, they congregate, and they multiply. The outputs multiply. Not the functions, the outputs. Let's look at an example. This one's a little bit different. We got square root of x minus 3 and the square root of x. So what is the domain of the square root of x minus 3?
Well, we can go...
Multiplies are red.
Yeah, we can plug in 3, but we can't plug in 2, right?
All right. Because 2 is going to give you negative 1.
Right. So then we're going to get from 3 to positive infinity, including 3.
Let me just say this real quick. Something that you can do. I mean, this is arguably not complicated. But if it were complicated, just like solve this inequality. When is that thing inside the radical greater than 0? Greater than or equal to? You're supposed to yell at me about the equal to's. That's your job. Your job is not to do the 400,000 things teachers do. It's to tell me when I forget my equal signs. I
forgot the less greater than or equal to sign, Mr.
All right. So you can always do that. Just solve that. I mean, you can do that down here as well.
X is greater than or equal to 0.
All right. So 0 to infinity. You were going to say something and I totally interrupted you.
I totally forgot.
All right. That happens. Our thoughts are fleeting. Now let's look at the product of these two functions, right? Function multiplication, right? The way we write this is f dot g in parentheses with an x. I don't know why I'm making that sound so much today. Hopefully it's not annoying.
It's a little annoying.
I'll try to stop. All right, so we're going to multiply these two things. And then let's go ahead and simplify this thing.
Wow.
What do you want to do?
Well, since we have something raised to a power times something raised to the same power, right? Because this is x minus 3 to the 1/2 times x to the 1/2, then we can use our properties of exponents and just have x minus 3 quantity times x, all raised to the 1/2 power.
Adding a little visual here, we just distribute that 1/2. That's what we do. All right, so simplify. Let me go all the way over here. It's going to be x minus 3 times x, all square rooted. All right, so I'm setting you up for failure here.
That's okay.
What's the domain of this thing?
Well, we would want the we want inside the radical to be greater than or equal to 0. So let's just set that up. And when would that happen? Well, yeah, we just set up our number line, just plug in some stuff. So like negative and like negative 20 is negative times negative, which is positive. 1 is negative times positive, so negative. And 5 million is positive times positive, positive.
Boom. So the domain of the product of f and g, you're telling me, is
Well, according to this number line, yeah, negative infinity.
Negative infinity to
0,
0,
including 0.
Including 0. And then including 3, right, to infinity?
3 to infinity, yeah.
Are we good? We should move on?
I don't think so, because remember that we were looking at our domains up over there? Yeah.
So let's check our answer. Right? Negative infinity. Pick a really, the biggest negative number that you can think of. Negative infinity is not a number.
Negative 17.
Oh, that's pretty big. I can't think of anything larger than that. So if I go back into the original function right here, negative 17 minus 3, that's, oh wait, we just found a larger negative number. Brain's exploding.
Oh, quadruple take.
I hope my picture was there and it wasn't just you. And then so square root of negative 20 times negative 17. Wait, undefined times undefined is defined?
No.
No, it's not.
No.
Right? This comes back to the idea of what we're doing. Right? When we talk about these types of functions, the product of functions, you can simplify it all you want. It makes it easier to interpret. But at the end of the day, the domain of the product of functions is exactly like it was in addition. It's the intersection of these two functions. These two functions' domains. 3 to infinity. Right? 0 to infinity. Intersected. Let me actually get, that's the and symbol. Let me get the intersection symbol. Pretty much the same thing, but little differences. And we care about little differences in math. Right? We're looking at the intersection of these two things, and that ends up just being 3 to infinity. There's our answer for product function products, function multiplication. This lesson is very rooted in what do we mean by f times g of x? And what we mean is that we're operating on the functions and then combining their outputs, not combining the functions and then getting a new function with an output. Right? We're not losing the meaning of f and g. They are still very relevant. If I wanted this function, I would just call it something new. I'd call it like h of x. Right? F times g of x. I'm telling you that f and g both matter. All right, let's proceed. Function division, a little bit different than function multiplication, which was a little bit different than function addition. All very similar though. Right? Same thing happening. We're plugging it in. Boom, boom, boom. Right? But there's an extra step that happens here. Right? If I plug something into G and it works, awesome. Plug something into F, it works, awesome. But there's a scenario that we need to care about. Can you identify what that scenario is?
Well, weren't we saying earlier that we needed our denominator to not be 0?
Right.
So what happens if like you plug x into G, you get out 0 as your output of G of x?
Yeah, let's say like F gives you 47, my favorite number, arguably the best number ever. And then G outputs 0.
Whoa, that's bold. I don't know about that.
Bold moves by bold people. 47 divided by 0, what does that end up being?
Undefined, also covered by our heads.
All right, let me write down here. Hopefully the BAM isn't covered. 47 divided by 0. 2 BAMs.
Bam, bam.
All right, 2 BAMs, because you should not forget that the denominator of your output cannot be 0. So the domain of this is going to be a little bit different. Right? We still care about simplification and how that doesn't change. If you think back to when we simplified rational expressions a long time ago, all the prompts said, don't forget restrictions, don't forget restrictions. This is one of those places where we start to care about writing down the restrictions.
And most of your comments on that classwork were you forgot the restrictions.
My class too. My class too. You know, we can only take so much blame. Anyways, proceeding. Domain of the square root of x. We've done that one. Let's just keep it going. The domain of x minus 4. That's
Everywhere.
yeah, all real numbers, right? I was
Yeah.
trying to think of a joke, but couldn't. Oh, by the way, I don't know why it took us so long to figure this out, but I'm just going to go ahead and do this for the viewer. We spent half of a class in I think it was my 4th period. I'm not sure. Trying to figure out how to write the blackboard bold R in Kami.
You figured it out?
You're going to hate what it is. It's capital R.
What?
It's just capital R.
So that's really interesting because that's a command that I had to add manually to my LaTeX.
Yeah.
That's great.
Let me make this bigger. If you do capital RE, it gives you something called the real function operator, which is, I don't know what it is, but you guys can look at it in, I'm trying to make this bigger is what I'm trying to do.
I thought that was something with,
I don't know much.
like
do you know anything about this?
Complex numbers and then you want the real component.
Oh, okay.
Where I'd seen that before. But I could be wrong because that looks really fancy. Much fancier than my professor's handwriting on a chalkboard.
True. But just a capital R.
Boom. Beautiful.
Yeah, so we added it to the database that we have going on our Canvas pages.
Nice.
So, and we added all of them. Complex numbers, natural numbers, all of them. So thank you to, I'm not going to say with the period because I can't remember exactly, but thank you to the people that figured it out. I did it again, sorry. All right, here we are, right? Little digression there, but I think it's going to be useful to many of you who don't want to write negative infinity to infinity tons of times. You can now use that. F divided by g. Let's get this function written out. It's as simple as writing the two functions on top of each other. Right? And we could go and simplify this. I don't know how we do it, but at the end of the day, the domain is going to be the intersection of the first function with the second function plus one thing. What was it?
When we're excluding when the denominator is 0. So x minus 4 equals 0 when x equals 4. So we can't include that. So our domain, I think, is from 0 to 4, not including 4, and then 4 to infinity.
I was about to do it again, but for you guys.
I was going to yell at you.
Well, you can't.
Hey.
See, I don't want to see, look, the little pointy part. I don't know. I can't avoid it. That's why I don't like it, to be honest.
I think you did it well the other times.
I just need to be, I'm not like patient enough to slowly write it well. All right. Oh, by the way, just as an aside to you, and I guess everyone that's listening, but I was talking to my brother the other day, and he told me he watched the entire pirate video.
Wow.
Like no interest. Well, no, I wouldn't say no interest. He works in a finance industry, so math is very important to him. But he wasn't too concerned about the topic that we were talking about. But he watched the entire thing.
Wow.
I was very flattered.
I told my brother, and he didn't watch it.
Well, what a lame brother.
He also forgot what factoring was, but that's okay. He's a dentist now. Whatever.
A dentist. All right. Okay. Here we are. We've kind of leading up to this topic, function composition, because it's a little bit more complicated than the other ones. And the notation, it's kind of annoying. All right. F of G is what we say. F of G. And I guess you could go one further and say F of G of X. But like if you think about it, if I say, hey, how would you say that? You'd say F of X. Okay? I'm now saying F of G. And what this notation here, I'm glad we actually have this document here so you can see what it's actually written as. It's not an O. It's a tiny circle that's raised above the bottom line. You can think of it as an O. But this represents composition, and it's saying work backwards. Start with G, then with F, and then we could do this for as many as we wanted. There we go. I'm erasing that, and I'm going to make sure I don't draw where our faces are. I could have F of G of H of L of smiley face. I don't know. Right? This is just saying evaluate the number with the first function, then, the furthest to the right function, and then work your way from right to left. And what it's saying is just plug it into the first function, evaluate it, get a new number, plug it into the second function, evaluate it, get a new number, and that's what gets spit out. And then this cascading effect happens depending on how many functions you have. Right? Function composition. We are composing functions, putting one function within another. Let's look at it with this. All right, let's knock out these domains real quick. What are they?
Negative infinity to 4, and then 4 to infinity.
I did it, but you didn't say anything.
I laughed.
All right, I did it that time. Yeah, that's pretty good too. That's pretty good too.
Better. All right, and then g of x's domain is 0 to infinity, including 0.
Cool. All right.
You just made that a face. That's not a negative infinity anymore. Mr. Kerr, you're setting a bad example for the children.
I think I'm setting a great example that it's really important to find little things in life that bring you joy. And drawing little faces on my infinities does that for me. Just don't tell me what to do. All right, so
lose points for it. It's fine.
f of g, we have g of f. Let's write these things out. All right, how do I do this?
I think
let me write it before we do anything. Sorry, let me write f of g of x. I think that might be helpful.
Yeah, because then we can think about g of x as something that's going into f of x.
It's like f of, what is g of x? The square root of
g
x.
G of x is root x. So then whenever we see x in our original f of x, we just have root x instead.
Right. Another way to think about it is I could also do it this way. 1 over g of x minus 4. We know what g of x is. It's the square root of x. But these are all the same thing. All right, let's get the domain of this thing.
The domain looks like, well, the denominator is going to be 0 when x equals 16.
We could whatever you want to. You can always set up an equation to make it easier too. Let's get that out of the way. It might not be necessary here, but you look at this. If you don't see 16 right away, you can always just go, well, when is the denominator 0? Solve the equation. Right? This is one of the reasons why we care so much about solving equations, is they allow us to solve other situations. But we're turning an idea, we need to figure out when this is undefined, that's abstract, into algebra that you've been doing since 3rd grade, maybe even before. All right, square both sides, and we get 16. So that is the number that's not allowed. So actually, sometimes I even like to put slashes through these equal signs. This cannot be 0. This cannot be 4. This cannot be 16. So the domain, it can't be 16. So that's one thing. Do we have any other issues?
Well, we also need x to be non-negative because it's inside a radical.
So we need to start at 0.
Go to 16.
Go to 16.
Not include 16, and then go up to infinity.
And for the fans, boom. One thing I want to add is just we can also take the thing under the radical and make an inequality and not forget the equal sign. Right? It's not necessary here maybe because you can see that it's just x. But one of the things that I find to be a really good strategy, and I'll reiterate this when we get to some examples in a second, is setting up these equations and just solving them, and then set it and forget it. Just solve it and don't even worry about too much of the concept. Just set yourself up an equation and solve. Let's get this other one. All right, they're the same thing, right?
I don't think so. G of f of x. So now wherever we have g and then parentheses f parentheses x. So now what's our input for g? It's the function f of x. Wild.
And then that becomes the square root of
a really big square root of 1 over x minus 4.
Yeah, I don't know why it was so big, but it just is, Let it be.
So now,
all right.
Well, our denominator is going to be 0. We can set that up as an equation. X minus 4 equals 0. Or not equal. Yes,
Yeah.
thank you, Mr.
Not,
Garrett.
not, not, and over the years, I've kind of become a little bit more relaxed about. My first year teaching, I was like, must have a slash because that is. But over the years, I've been like, you know what? Do you? Just make sure that you interpret the way you do it correctly.
Hmm.
So I'm going to put those slashes there because it helps me interpret my final answer a little bit more easily.
It's reasonable.
All right.
And then inside our radical, we need that to be non-negative.
Yeah.
So
So
all of
let's
that needs to be greater than 0
1 over x minus 4 needs to be greater than or equal to
or equal to.
0.
But can it equal 0?
Okay. This will never equal 0. This will never equal 0. If you think about the graph, it's a 1 over x graph that we're shifting. It's never going to be 0. It's going to get closer and closer to 0 as x gets bigger, infinitely big or infinitely negatively big, but it's never going to get there. But I can't put this on a number line and then just do my solving. I believe it's going to go from negative to positive, right?
That sounds good. Yeah, because there's no reflection happening.
A lot of what we're talking about is coming back. Like there's many ways you can think about a lot of things that we've done visually and non-visually. All right, so it can't be 4, and it must be, we need to be positive. It must be, I'm really getting closer. Yeah, I could stroll down a little bit. It must be bigger than and not inclusive 4. So we need the combination of these two things, the intersection of these two things.
And that's
4
to infinity. Yeah.
4 to infinity. Cool. All right, and I don't like that I did this side in red and this side in blue. It's not symmetric. It bothers my mind, but I bet you bother some other people too. Whatever. We shall move on. All right, so what is one last thing we can take away from this page, though?
Oh, wow, look at that. It's purple. That might be covered by our heads. We might have different functions,
This is
and
whatever.
we might have different domains depending on the order of our composing.
The order of composing matters. F of G and G of F. Fog does not equal Goff. Fog does not equal Goff. All right, F of G does not equal G of F.
Goff equals spit.
I bet the viewer could find some functions that do equal each other, but it is not guaranteed. What do we call this property? Switching the order.
That's a thing. It's like a thing when you're like driving and you're going there and you're going back. Like commute.
Yeah, this is my attempt at a car. Here's Blair.
Is that under our heads? It might be.
Oh, it totally is. I need everyone to appreciate my little picture of Blair, though. A little
I like this fire. It's nice.
Yeah. So commute. I don't know how this helps us remember that it's called commutativity, but let me also make sure that everyone can see commutativity. Commutative. These are not commutative. All right, function composition is not commutative. Function division, not commutative. Right, function multiplication, function addition, those are commutative.
Because those operations are commutative, but division is not a commutative operation.
No. And composition. I think the most important thing here is a composition is not commutative. All right, fun story for your class. I told this my class this already, but there's a student that used to go to Blair, Eric Agard. He was on Jeopardy, and there was a math round, and then all the math teachers at Blair were like, "Yeah, he's gonna do great." Magnuson went to Blair, math round on Jeopardy, gonna make all the monies. He got the commutative question wrong. The question was, what do you call when x times y is equal to y times x? Like, what is that property? And he goes, associativity. I think. I don't actually know what he said. I think he might have said inverse or I don't know. Watch the episode. I think it's on Hulu. I wonder if he'll ever see this. Anyways.
Facebook.
Yeah. Commutativity, x, y, y, x. Right? Hopefully he knows that his mistake has been educating students for the past 2 years.
And that's the goal, really.
Yeah, right. Was it worth $1,000? I don't know.
I mean, it might mean payouts for these students. So
that's true. Yeah. So he's made $1,000 at least across a bunch of students, although they had not probably made money off that knowledge yet. All right, let's do some examples and then we'll get out of here and get in, get out. Function division. What should I do first?
Can we just put like 5x over x and then cancel out, and because we can simplify, and simplifying is 5?
Yeah.
Yeah?
Yeah. No.
No.
Can I erase that? No, I can't. I have to delete it.
Wow, it's really annoying.
I'm really lazy. You know what I'm gonna do? We can cancel. Like, this helps us interpret the function a little better. F divided by g of x is a function that is identical to the function 5, the horizontal line 5. But it doesn't work at 0. This function, f of g of x, is going to look like this. So we do need to be careful. The answer here is negative infinity to 0, and then union 0 to infinity. Another way you could have written this is, oh, I did erase. Oh, whatever. You could do this. There's lots of things you could do. All right, cool. Let's do another example. Let's just knock these out.
All right, so F
we actually, before we continue, we do encourage you to pause the video and think about how to solve the problem. Pause the video, think about how to solve it, maybe solve it yourself, because at the end of the day, these videos, they're teaching you stuff, but the most that you will learn comes from diving in and trying to swim. So try to do these problems first. We're going to start this in 3, 2, 1. Mrs. Contreras.
F of g of x means we are taking the square root of g of x, which is negative root x. And that is always going to output negative number. G of x is always outputting a negative.
My first inclination says this is impossible. No matter what, we're going to get a negative number, and the square root of negative is undefined. Bam!
But I think we also need to consider 0.
Always consider 0. You know, 0 is always forgotten about. I feel like there was a Cyber Chase episode about that. Did you ever watch that show, Cyber Chase?
Oh, yeah, with Motherboard. And
yeah, I feel like there was an episode about like a lonely 0 that like no one cared about.
That's
0. So don't forget about 0.
Don't forget 0.
And the square root of 0
into that, what do you get? You get
boom.
0. And it's
Singleton
like
said. Boom.
Set.
Yeah, get that vocab flying back. Excellent. Zoop. That one's done. We're going to start this one in 3, 2, 1. G of f. G of, oops, I was about to literally write the word f. Of. G of f of x. It helps to say it out loud, I think. G of f. G of f. And then we're just going to take that function f of x. And what's it going to look like?
We're going to do 1 over square root of 4 minus x, and then minus 2 after that.
All right. The domain of this one's a little bit more tricky. What are the two things we care about?
When the denominator equals 0.
So when 4 minus x, that's a terrible minus sign, but I'm not going to fix it. Minus 2 equals 0. We want to get rid of those.
Sometimes I like to be lazy and just do root 4 minus x, and then is not equal to 2.
I'm cool by that. You cool by that?
You're just going to like smush it over anyway. It's fine.
Yeah. Get some steps going in
the not equals.
I'll put it.
And then square everything.
Square everything. Oh, we're going to solve it. Okay, square everything. 4 minus x cannot equal 4. Do a little bit of boom, boom, boom. I believe that ends up being 0.
0.
Yeah. And move the 4 over, get a 0, negative x equals 0. That's 0. Cool. So we care about when the denominator is 0. What else do we care about?
When inside our even radicals, we have, we want to make sure we have non-negative values.
All right, so this one's pretty simple. We need to know when x is greater than or equal to 4. So we need both these two things to be true, and it looks like that 0 never mattered.
Greater than or equal.
Wait, did I make a mistake?
Yeah, because when you You flipped the signs, but you didn't change the direction of your inequality.
I'm going to add x to both sides, and I get that. When is
There
x
you go.
less than or equal to 4? All right, I guess technically, if I'm going to be picky, I should be doing slashes through this, but I'm not going to do that.
Gosh, that's so much.
I know it is a lot. I know. I'm realizing, and that's kind of one of the reasons why I stopped caring over the years. All right. So when is x less than 4, and when is x not 0? That's our domain.
From negative infinity to 0, not including 0.
Mm-hmm.
And then 0 to 4, including 4.
Awesome. Sweet. I love this problem because this problem is going to exemplify. Watch, everyone try it real quick. 3, starting 2, 1. This problem exemplifies why f of g and g of f being different matters a lot, because I think this one's way harder. F of g, what does that end up being? I've lost what my f and my g are. I'll keep it just enough. I'm going to jump straight to the function here. F of g, I'm going to have the square root of 4 minus 1 over x minus 2.
Whoa.
It's a lot.
That is a lot.
Right? All right, what do we care about?
Our radical having non-negatives.
All right, so we want 4 minus 1 over x minus 2.
Greater
Needs to be greater than or equal to 0. We know how to solve that.
Yeah, we do.
We spend an entire block trying to solve that. All right, what is the first step? Multiply both sides by x minus 2?
Sure.
Why would multiplying by x on both sides be a bad idea?
Both sides of the inequality.
Yeah, what I was about to do, yeah.
Denominator.
Okay. Should I multiply both sides by x minus 2?
No, because then we'll lose information.
Yeah.
Of x can't be equal to 2.
And also, what if x is negative?
Oh.
Then you have to flip the sign. See, then you have to take cases. You'd be like, what if x is negative? What if x is positive? Solve two things, combine them at the end. Instead, let's keep everything on the left-hand side. That doesn't do anything to the inequality sign. Multiply the 4 by x minus 2 over x minus 2. That's just 1, right? Regardless of whether x is x positive or negative. When you divide two of the same number, you always get positive 1.
It's an identity property, right?
Of equality, yeah. And then, all right, so now we just need to just continue doing this inequality problem. We're going to get 4x minus 8 minus 1 minus 9. X minus 2 needs to be greater than or equal to 0. This is a little bit obnoxious, but it's necessary to know when this function is going to be defined. So what are the two values that we care about? I believe 2 and 9/4.
9/4, yes.
So which one of those is bigger?
9/4 is like more than 2. Because
I'm also kind of mad.
is 2.
Yeah. Sweet. All right, and then when I plug in a super duper negative number, what do I get?
Negative over negative. Positive.
Negative over negative, positive. And then I don't want to plug something in between 2 and 9/4. I don't want to plug in something like 2.0001. I guess I could.
Yeah, I mean, you could, yeah.
But I know something's going to happen. When I pass 2, the denominator is going to be, you say it.
The denominator sign changes.
Yeah, but the top doesn't. So now we have a plus and a minus. That's going to be a minus. And then once I pass 9/4, the top switches to plus. It's alternating here. Let's take advantage of that. Right? So so the final answer is negative infinity to 9/4 to infinity?
Yes. But which one are we including and which one are we not?
What do you mean?
Well, because like, if we plug in 2, we're going to get undefined.
You got undefined, right?
Can't include 2, but we can include 9/4.
But we can include 9/4, absolutely. We care about when this expression is undefined, but we've already got rid of 2, so we don't have to worry about that. Negative infinity, 2, 2, can't be 2. We have an undefined problem. Union, 9/4, it can be 9/4. What happens when we plug in 9/4 is we get 0. We get 4 minus 4, which is 0. And then we go to infinity. Sweet. Bingo. Awesome sauce. Man, Man, I haven't said the word awesome sauce in years.
So,
I don't know why I just said it. Just
because it's
popped in my
on
head.
fleek.
Oh boy, we let's not go down this. Let's not go down this. It can't be 0, but it can be 9/4. Let's not go down that road. All right, so we got one more here, and we are not going to put any more questions in this video lesson. No more questions that are going to pop up. So if you feel good, you can go ahead and hit the. I don't know. I did it again. You can go ahead and finish this.
The pop sound was that? Yeah.
I hope that was really good. It felt good. We're gonna do this last one here, but if you would like to, just if you don't want the video to be too long, you can check out here. But we highly encourage you. Part of being in the magnet math sequence is this intrinsic motivation to strive in math class. So we do highly encourage you to attempt this problem. There's all the things we've talked about are about to happen, and it's a tough problem, and we want you to develop over time this drive to be able to solve complex things. Okay, so we don't want the video to be too long, so we'll do challenging ones in class, but we're going to do this one here for you only if you want it. Let's go ahead and get started in 3, 2, 1. F of g of h of x. Just f of g of h of x and 1, 2, and ready. Here we go. All right.
Anyway, so h of x is x squared, so that's getting composed inside g of x, which is
Okay.
11 minus x. So then we're getting
Watch
f
this.
of root 11 minus x squared.
So what I'm going to do, I hear what you're saying. I'm going to write f of x, but when I see an x, I'm not going to write anything. And then now I'm going to put in g of x. But when I see an x, I'm not going to put anything. And then when I need to put an h of x, that should be, yeah, that's an 11. I'm going to put an x squared. And I think this is what you were saying, right?
So you just did all of the compositions in one step, and you kind of went from right to left. No, you went from left to right. And even though you'd said to go from left to right, but clearly it works both ways as long as you get your ducks in a row.
As long as you know, as long as you understand what composition is saying, that you're putting functions within other functions, you can write it down however you want. A very methodical way would be to go from right to left, write the function. Another thing you could do is write h of x, and then write g of x around it, and then write f of x around it. All these work, but the thing that you need to be worried about is just understanding what f of g of h is saying, because it is not. I feel like if aliens came to Earth and they saw that, they'd have no idea what we're talking about. If they saw 3 plus 4, I mean, they might not know what plus and 3 and 4 mean, but this is like quite abstract, whereas this might be a little bit more understandable. So f of g of h, your goal is just to understand what it means. All right, let's look at this thing. Let's find its domain. That's the hard part. Writing the function is easy with time.
So we need our denominator to be non-zero. So when is root 11 minus x squared equal to 3?
Right? If you sit and look at this function and try to just, in your brain, think about what the domain is, you're going to make a mistake. Right? Set your equation up like Mrs. Contreras is saying and just solve it, and you're done. We know how to solve square root equations. Square both sides.
Square everything.
When we square things, we do need to keep in mind that we might have extraneous solutions at the end. Just keep that in mind. I don't think we're going to here, though.
Root 2, right?
Wait. Yeah, root 2, because I'm going to subtract 11, get negative x squared equals negative 2. And then x squared is equal to positive 2. Divided both sides by negative 1. Just going to go ahead and put it over here. X is equal to the plus or minus the square root of 2. And I believe both of these are going to work because of that square. That square is going to solve our problems with the negative stuff. Cool, so we have two answers there, negative root 2 and positive root 2. Those do not work. That is when the denominator is 0. And what else do we care about?
When our radical is positive or non-negative.
When the radical is non-negative, right?
Or I guess what's inside our radical.
Yeah.
So we have what, like 11 is greater than or equal to x squared?
Yeah, and I'm going to write it like this. X squared is less than or equal to 11. Is that fair? Is that confusing? You tell me.
Sure. I mean, like, it's
the same
important
thing.
to build our mental flexibility
True.
of dealing with things.
The reason why I like my x squareds first. That's why I moved it around. All right, cool. So when is x squared greater than or equal to 11? Or sorry, less than or equal to 11?
Less than or equal to 11, that's, well, it's a parabola, right? So then we're going to get whenever, like, x squared is less than this horizontal line of 11. So that's what, plus or minus root 11. And between those.
Yeah, I like your graphical approach. That is absolutely something that a pictorial learner, a visual learner should use. The other thing I want to just bring to mind is how we did this algebraically. Whenever you dealt with inequalities, you moved everything to one side. You factored. Uh-oh, that's not factorable. Well, we could use the quadratic formula, or we can just realize that this is the difference of squares with a not perfect square. Right? X minus root 11, x plus root 11. Throw this on a number line, which is basically what you've done. I would argue that your way is better. It's much faster. If we care about efficiency, your way is thebomb.com. But if we want to do it the way that we learned the last unit, get your stuff on a number line, plug in something super negative, and then what do we care about? We care about when we're negative. Exactly what you said. With that said, right? Our negative root 11 and root 11, they count, right? We want them?
Yeah, because in our function, we'll just get 1 over 0 minus 3, which is still a number.
Yeah,
one
negative 1/3. Yeah. So wait, let's see. We got positive root 2, negative root 2, and we need to be between negative root 11 and root 11. Is negative
bigger?
root... What?
What's bigger? Like, what order do we put the roots?
Yeah, so let's think about it. What is root 11 between? We've done this before.
Root 11 is between root 16 and root 9. I said that in the wrong order. Root 9 and root 16, so 3 and 4.
So it's between 3 and 4. So it is going to be the most negative. We're going to go up to 2. Negative 2. No. Oh, and negative root 2. What are we talking about? Why are we checking? Negative root 2 is certainly less, right?
Yeah.
Okay. And we care about 11. We don't care about 2. And then what's next?
Negative root 2 to positive root 2?
Yeah, I was about to forget that. Between you and me and everyone watching. I was about to forget the middle positive negative root 2 to positive root 2. I was going to go straight to this one. I think I'm messing up somewhere.
You need a bracket on. Yeah.
Yeah. All right, there you go. There's combination and composition in the bag. Believe me, this can get difficult. But I think we got the basics in our pocket and we're ready to use them. All right. Whenever you're ready, just pull them out of your toolbox and then hack away. Where's Mrs. Contreras going? You back?
Yeah.
All right, cool. How do you want to close this one out?
Get your flu shot.
Get your flu shot. get your flu shot. And I got high hopes this year because everyone's thinking about it. Get your flu shot.
Every year, your flu shot.
Do I have any words of wisdom? No, I don't. Don't forget to challenge yourself to stay active. Stay active, stay mentally active, stay physically active, and stay emotionally active. Care about yourself. Right? I think that's one of these things right here. Care for yourself.
That is
All
so
right,
small.
those are my words of wisdom. All right, let's get this one out. Oh, wait, no, we did it again.
Oh.
Here we go.